Hello everyone, my name is Filippo Contro and today I'm presenting EtherSolve, computing an accurate control flow graph from Ethereum Bytecode. Ethereum has been growing exponentially over the last few years, both with the value of its cryptocurrency and with the volume of transactions in its blockchain. An important feature that it introduced are smart contracts, immutable and distributed programs which are executed on the blockchain and that can receive, store and send money. However, these smart contracts may have errors and vulnerabilities, which can cause huge loss or freezing of funds, like the famous DAO incident. Moreover, they are immutable, so errors cannot be patched once deployed. For this reason, there is a growing need for techniques and tools to analyze such smart contracts. The main objective of this work is to provide an accurate method to abstract the code of a smart contract, in order to have a solid base to perform any type of analysis. Our challenge is to analyze directly the compiled bytecode, so that we can process any smart contract deployed on the blockchain. This adds difficulty, as it is less clear than the source code, but let us analyze even closed source contracts. The main difficulty of analyzing the bytecode is the intrinsic architecture of Ethereum, as jump addresses are computed dynamically during the execution. Indeed, the current analysis tools show worrying amounts of false positives and false negatives due to an inaccurate representation of the code. Hence, we propose a new static analysis technique based on symbolic execution to model an Ethereum smart contract with a control flow graph implemented in EtherSolve. This example shows a simple smart contract written in Solidity, which is then compiled in bytecode. EtherSolve is then able to parse the instructions, perform a symbolic execution, and build an accurate CFG, which represents the code. EtherSolve CFG is enriched with the detection of the dispatcher, the entry block, and the common exit block to help subsequent analysis. Our procedure consists of different steps. First, the raw bytes are parsed into opcodes. Then, these opcodes are grouped into basic blocks, which are the nodes of the graph. They are groups of contiguous opcodes without any alteration on the execution flow, which can be brought by jumps and return statements. The opcodes are then executed symbolically in order to determine the possible destinations of the different jump opcodes, following a depth-first search in the graph. Then, the newly discovered jump destinations form the edges that are immediately added to the graph, performing an incremental build. Finally, the CFG produced represents the code behavior, and it is a base for subsequent analysis. As an example, we built a simple but effective detector for the reentrancy vulnerability using a pattern matching technique. Basically, a code suffers from reentrancy when there is a write on the memory after a fund sent to an arbitrary address. An attacker may direct this transaction to the contract itself, causing a leakage of funds, as the memory is never updated to confirm the transaction. Our technique consists in a search on the graph for storage access in write mode after a send to an address which cannot be statically determined. Here is a simple example of symbolic stack execution. Since the jumping instruction takes its arguments from the stack, we keep track of all and only the operation performed by the opcodes that manipulate jump addresses, which are push, dupe, swap, pop, and end. The other opcodes simply consumes and generates unknown elements on the stack, like the add opcode on number 40. In the example, the address of the jump on opcode 42 is pushed on the stack on opcode 37, but our algorithm is able to keep track of it. The full behavior is described in a lookup table. We conducted an experimental validation of our CFG building technique to test its accuracy. It consists of two phases, automatic and manual, and there is no exact way to determine the correctness of a CFG. We built a dataset of 1000 real-world smart contracts taken directly from the Ethereum blockchain with many different versions. Then we tested the similar tools from the state-of-the-art on the dataset, obtaining a common representation and computing the differences in the CFG produced. Finally, we proceeded with a manual inspection of some interesting cases to highlight the differences among the tools. EtherSolve can compute a CFG for more than 99% of the contracts in the dataset. The manual comparison showed that it is more precise than the others, being able to compute paths that the other tools cannot detect, but that corresponds to real paths on the source code. To test the accuracy of the reentrancy validator, we compared it with the results obtained by the Solidify paper. The authors injected vulnerable code inside some smart contracts, executing the tools and comparing their detections. Hence, we executed the EtherSolve on the same dataset, comparing our results with the state-of-the-art reentrancy detectors. The table shows that, despite its simplicity, EtherSolve is as precise as a Slither, which is currently the best tool for vulnerability detection. Moreover, EtherSolve is the only one which analyzes directly the bytecode, without any other info on the source code. The reasons behind its false negatives are due to contract inheritance and are detailed in the paper. Despite it will be very important to automatically analyze smart contracts and detect potential defects and vulnerabilities on the code, most of the existing analysis tools for Ethereum bytecode come with some shortcomings and limitations. For example, the accurate extraction of the CFG from Ethereum bytecode is very challenging due to engineering decisions on its infrastructure. Summing up, this work serves as a base for any future analysis on Ethereum smart contracts that need an accurate CFG to represent their code. And our reentrancy detector is an example of how accurate code models can produce accurate analysis with low effort. Thanks for watching.
Okay, thanks for watching the last video. Filippo is here to answer your questions.
Hello.
The first question is by Fabio, and actually I did the same question. So your approach is amazing because you can do intercontract control program creation. But then I wonder, what is the efficiency of your approach?
Well, in terms of a performance meant by time needed for the analysis, we measured about 1 second almost for each analysis for each contract. Obviously, there are some huge cases where the time grow up to 5 or 10 minutes, but on the average is a pretty fast technique.
Another similar question is, when I read about using symbolic execution in testing, then one of the main limitations that it doesn't scale up. So basically it works, but only on limited subsets. But then I mean, when reading your paper, I was a bit surprised because of the same reason I said before. So why do you think that it works in this case? Well, what are the differences?
In our opinion, the reason is that there are only 6 opcodes that treats jump addresses, which are the core of our analysis. Which, I mean, they are the target that we discovered in order to build the CFG. So having only a little subset of opcodes which deals with such addresses simplify the symbolic execution. Obviously the biggest problem that we found was the increase, the growing stack.
Okay.
As the maybe a recursive or loops or cycles in the graph, let the stack grow, but we then approximate on the comparison to avoid such paths.
Super cool. And then I presume that once you have this control flow graph, then you could implement even other vulnerability detections.
Yes. In fact, the target is to build a CFG, as there are many tools and techniques that use a CFG. So a precise CFG could lead to easy, precise analysis.
Thanks a lot, Filippo. So
thank you.
We are going to watch the next video in a few seconds, and see you in a while.
Thank you.